In 1952, the Pennsylvania Railroad delivered Alco an ultimatum no locomotive builder should ever have to hear. Remove every single one of your engines from our property, or we will never buy from you again. After over 50 years of locomotive building, Alco had even built tanks that helped win World War II. And now their biggest customer was threatening to ban them forever. Not because their locomotives were too slow or too expensive, but because there was something dangerous within their engines. The engine behind all of it was the Alco 244. It was supposed to be the engine that secured Alco's future. Their engineers proposed a turbocharged V-type diesel, with cylinders arranged in two banks forming a V shape, just like a V8 car engine, but on a completely different scale. These engines would power everything Alco had to offer: the FA and PA cab units, the RS2 and RS3 road switchers, and the RSD series. The 244 wasn't just an engine. It was Alco's entire diesel strategy in one design: a 9-inch bore and a 10.5-inch stroke. Each cylinder displaced 244 cubic inches. That is where the name came from. In its V12 configuration, it produced 1,500 horsepower. The V16 pushed out 2,000 horsepower. But here is where the problem started. They began with decisions that looked smart at the time. EMD cast their engine blocks as single pieces, one massive casting, one solid structure. Alco could not do that without investing in foundry equipment it did not have. So Alco welded its 244 engine blocks together from separate components. The main bearing saddles, the structures that support the crankshaft and the backbone of the engine, were welded directly into the block. It was cheaper, faster, technically innovative for the 1940s. But welded joints create stress concentrations. Every time the engine heats up and cools down, the metal expands and contracts. Those welded bearing saddles, under constant load, were exactly where cracks would form. Alco tested the welded blocks. They passed, in controlled factory conditions, on short duration runs, at moderate temperatures. What Alco did not test was what happened after thousands of hours of real-world punishment. But the block was only the beginning. Alco designed their crankshafts in both cast iron and forged steel versions. Cast iron was cheaper. Forged steel was supposed to be stronger. But the forged steel crankshafts arrived from the supplier with metallurgical flaws, microscopic impurities embedded in the steel that would slowly propagate under the repeated stress of turbocharging, V-configuration vibrations, and thermal cycling. The first 20 production Alco 244 engines told Alco everything they needed to know. Every single one required a complete rebuild with new forged crankshafts. All 20 were rebuilt within months of entering service. That should have stopped production immediately, but Alco believed better forgings would fix it. They were wrong. Even the improved crankshafts continued to crack, especially in the 12-cylinder models. Then there was the design choice that seemed minor but proved catastrophic. Alco routed their high-pressure fuel pumps in a way that allowed leaks directly into the crankcase. And high-pressure fuel pumps always eventually leak. When they did, diesel fuel diluted the lubricating oil. Diluted oil couldn't protect the bearings. Unprotected bearings failed. Failed bearings stressed the crankshaft. And a stressed crankshaft, already compromised by bad metallurgy and already sitting in a welded block developing its own cracks, broke. Every flaw fed the next. It was a chain reaction designed into the engine from the start. So why did Alco ship it? Because they had no choice. Or at least they believed they had no choice. By 1945, EMD had already delivered over 1,000 diesel locomotives. Baldwin and Fairbanks Morse were entering the market. The steam era was over, and railroads wanted diesels now. Alco's executives demanded results fast. From initial design to production, the 244 took roughly 2 years. That's extraordinarily fast for a completely new engine. EMD had spent years developing and refining their 567, but Alco compressed everything, including design validation, prototype testing, material verification, and long-duration reliability testing. They believed they could fix problems in the field, and for the first few months, it looked like they might be right. The engines passed acceptance testing. They ran fine through the early weeks of service. Individual components all seemed sound. The turbocharger worked. The blocks held. The bearings seemed adequate. But none of these problems showed up in the first few thousand miles. They were time bombs. The welded bearing saddles developed hairline cracks with each thermal cycle. The crankshaft defects slowly propagated. The fuel pumps began to seep diesel into the crankcase. 10,000 miles, 15,000, 20,000. And then the failures did not trickle in. They erupted. All at once, across the entire fleet. Between 1946 and the early 1950s, Alco built somewhere between 1,500 and 2,000 of these engines. And now, every single one of them was becoming a liability. By late 1947, Alco's service department was drowning. The problems that had been invisible during factory testing were now erupting across the country, and they were erupting all at once. The crankshafts went first. Alco had already rebuilt the first 20 production engines with supposedly improved forgings, but the replacements were cracking too. Field representatives were finding the same pattern in engine after engine. Hairline fractures radiating from the journals, surface defects, metallurgical flaws that no amount of redesigned forgings seemed to fix. Both the cast iron and forged steel versions were failing. The 12-cylinder models were the worst. Then the blocks started cracking. Mechanics running routine coolant pressure tests watched coolant seep, not from hose connections, but from the block itself. Cracks formed right at the welded bearing saddles, exactly where the welds met the block. A cracked block was not a repair. It was a complete engine replacement. By early 1948, Alco had replaced roughly 600 cracked engine blocks in brand new locomotives, some with less than 20,000 miles on them. Each replacement meant a full locomotive teardown, a new block, a complete rebuild, and testing. That cost was $15,000 to $20,000 per unit, all under warranty, all on Alco's dime. The welded block design that was supposed to save manufacturing costs was now costing 10 times more in the field than cast blocks would have cost in the factory. While mechanics tore down engines to replace blocks, they discovered something else. The oil smelled like diesel fuel. High-pressure fuel pumps were leaking past their seals directly into the crankcase. Not visible external leaks you could spot and fix, but internal seepage that silently diluted the lubricating oil. Diluted oil could not protect bearings, and bearings failed. Failed bearings stressed already compromised crankshafts. Diagnosing the problem required pulling the entire engine from the locomotive. Railroads were sidelining brand new units for weeks just to find the source of contamination. Even the turbochargers were failing. General Electric had developed the RD1 specifically for the 244. This was not proven technology adapted from other applications. It was new hardware bolted onto an already compromised engine. Compressor wheels cracked. Exhaust manifolds overheated. When a turbocharger seized, it sent metal fragments into the intake system, and the engine lost power entirely. Each General Electric redesign meant another round of field modifications to every 244 engine in service. Railroad crews started calling the 244 powered locomotives honorary steam locomotives. They smoked like steam engines. They broke down like steam engines. They spent more time in the shop than on the road. The diesel engine that was supposed to prove Alco could compete in the modern era was making their locomotives perform worse than the steam engines they replaced. For Alco's management, the nickname was not a joke. It was the sound of a reputation collapsing. Alco's engineers knew what had gone wrong. Every cracked block, every failed crankshaft, Every fuel-contaminated crankcase. They had cataloged all of it. And in 1949, they started over from scratch. The new engine was the 251, named like its predecessor for its cylinder displacement. Each cylinder displaced 251 cubic inches. It was available in V6, V8, V12, and V16 configurations, with the 12-cylinder version producing 1,800 horsepower. That was 300 more than the 244, from an engine designed to actually survive real-world service. Everything that had failed on the 244 was redesigned. Cast engine blocks replaced welded constructions. Single-piece castings with no stress concentrations at the bearing saddles. Properly forged crankshafts came from a different supplier with verified fatigue resistance. A fuel system kept diesel fuel out of the crankcase. A commercially proven turbocharger replaced GE's custom design that had never worked right. But the biggest change was not engineering, it was patience. The 244 had gone from initial design to production in roughly 2 years. The 251 took 5. 5 years of development, testing, and validation went into it before Alco released it to a single customer. They ran it in desert heat and mountain cold, in heavy freight and high-speed passenger service, thousands of thermal cycles, and hundreds of thousands of test miles. They were not going to make the same mistake twice. In 1954, the Milwaukee Road agreed to test the 251 in service. This was significant. Milwaukee had been one of the railroads most damaged by the 244 catastrophe. Their mechanical superintendent was deeply skeptical, but he gave Alco one last chance. The results were everything Alco needed to hear. 180,000 miles between major overhauls. No crankshaft failures. No cracked blocks. No bearing catastrophes. No fuel contamination. Milwaukee's mechanics were genuinely impressed. But the 251 was not perfect. Under heavy road service, it had a tendency to overheat. Some railroads found the problem serious enough to demote 251 powered locomotives to switcher duties, where loads were lighter and more predictable. The 251 was good, much better than the 244, but it was not bulletproof the way EMD's engines were. And that was Alco's tragedy. They had finally built a reliable engine. They had done the testing. They had fixed the flaws. But for the railroads that had been burned by the 244, the railroads that had replaced 600 engine blocks under warranty, that had sidelined brand new locomotives for weeks, that had watched their crews nickname Alco's diesels honorary steam locomotives, much better was not enough. Those railroads had already signed their next orders with EMD. The 244 had not just failed as an engine, it had destroyed something that no amount of engineering could rebuild: trust. Today, very few 244 engines survive. Most were scrapped in the 1950s. Some 244 powered locomotives were saved by swapping in 251 engines. The frames were sound. It was only ever the engine that was the disaster. A handful of RS3s and PA cab units sit in museums with their original 244 engines intact, maintained by volunteer crews who will tell you the fundamental design flaws never really went away.